Hey, today we're going to talk about continuity and one-sided limits. Okay, so continuity occurs when three conditions are met. The first is that f of c is defined. The second is that the limit as x goes to c of f of x exists. And the third is the limit as x goes to c of f of x equals f of c. All three of those things need to be true. So I need to be able to do direct substitution in this. Now, you can kind of think of continuity as, can I draw the shape, or can I draw the curve without picking up my pencil? If I can, it's continuous. But I need to make sure there's no sharp corners, okay? No gaps. Okay, so continuity on an open interval. A function is continuous on an open interval AB when the function is continuous at each point on the interval. Now remember, this is interval notation, so A is one point on one end of the interval and B is a point on the other end of the interval. A function is continuous on the entire real number line from negative infinity to positive infinity is everywhere continuous. Now there's two kinds of continuity. One is called removable, the other one's non-removable, okay? So here's a couple of examples of removable. Here's a curve, it's got a hole in it. If I just plug that hole, then I have a continuous function. That's removable. This one's almost the same, but slightly different. This one goes along, and then it drops down to here, and then it comes back up and goes in. If I could take this point right here and slide it up and put it inside that point, then that thing would be continuous. These are non-removable. This curve is one curve from I don't know, -2 to 1 here, and then it's a different curve completely from 1 to infinity, and this thing has a big, huge gap in it. Okay, I can't pick this whole graph up and move it. There's not a single point that I can do to, like this one, just plug the hole. This one is also non-removable because it's got an asymptote right in there. Okay, so that's the two types of discontinuity that you will hear about. One-sided limits. So we say the limit as x goes to c from the positive side of f of x equals L. That means that, this just spells it out right here. The limit of f of x as x goes to c from the positive side. So you got a little plus right here. Notice this one, the only difference is got a little minus. That means that it's the limit of f of x as x goes to c from the negative side. Now, we already looked at a couple of functions last class where the limits were different at these two things. When the limit from the left and the limit from the right are not equal, then the limit does not exist. Okay, so you can have a left side interval or a left side limit and a right side limit. If they're the same, then the function has a limit as a whole. But if they're different, then the function does not have a limit as a whole. Okay, so the limit of f of x as x approaches c exists if and only if the limit as x approaches c from the positive side of f of x is L, and the limit as x approaches c from the negative side of f of x is L. Okay, so let's look at this. This is the greatest integer function. So just to kind of remind you what that is, the greatest integer function, it's 0 everywhere until it reaches 1 and then it jumps. And it stays 1 until it reaches 2 and then it jumps. So you get this, they call this a step function because it looks like stairs. You can see it's open on the right and closed on the left. Okay, and it's written like this. What is the limit as x goes to 1 from the negative side of f of x? So what I do is I go here and I look at 1 and I go from the left side. This has a limit, and that limit is 0. Because this thing's always 0 until it reaches 1, then it jumps up to 1. Now, what's the limit as x goes to 1 from the positive side? So from this side, that is 1. So this has two different limits. This function does not have a limit. at any of the integers. It has a limit in between. So if I wanted to know what's the limit of this function f of x at negative 1.5, well, that would be right here, and it would have a limit of negative 2. Okay, anything else? Nothing else on this page. So, continuity on a closed interval. A function f is continuous on a closed interval ab. So remember, these brackets here, they mean that a and b are included if those are curved. Parentheses, then a and b are not included, but it's everything right up to a and right up to b. The function f is continuous on the closed interval ab when f is continuous on the open interval ab, and the limit as x goes to a from the positive side of f of x equals f of a, and the limit as x goes to b from the negative side of f of x goes to f of b. Okay. The function is continuous from the right at a and the left at b. So let's talk about the continuity of this thing right here. This is a half circle, a semicircle. Looks a little weird because the graph is not perfectly scaled. But so what kind of continuity does this have? Why don't you take a second, think about it, write down your own answer, and then we'll talk about it in a second. Okay, so this thing, you should have determined that the function is continuous everywhere along this interval. So definitely every spot in between here is continuous. I can draw the entire thing without picking up my pencil. It meets all the criteria that we had on this page. Okay, f of c is defined everywhere. There's no holes in it. There's no asymptotes in it. The limit as x goes to c of f of x exists, and the limit is f of c. So the places you really got to consider are the endpoints. Everywhere in between here is obviously continuous. So is this continuous, or does this have a limit from the positive side, from the right side? Yes, it does, and that limit's 0. Does this have a limit from the left side? Yes, it does. That limit is 0. So this is continuous everywhere. So we can just write that down. F of x is continuous everywhere on the interval -1 to 1. Okay, we have a theorem. If b is a real number and f and g are continuous at the point x equals c, then the functions listed below are also continuous at c. So I can take a scalar multiple. So what that means is if I had the function x, y equals x, that is continuous. It's just a straight line, okay? And that also means that 3x is continuous. The sum or difference. So let's say I had a function f was 3x and g was x squared. Okay, if I add those two together, that function is also continuous. If I subtract those two functions from each other, they're also continuous. If I take a function, say 3x, and another function x squared, they're both continuous, and I multiply them together, I'm going to get a third function, 3x cubed. It is also continuous. And finally, if I divide them, so let's say I took 3x over x squared, okay, and I simplified this. This is going to be continuous everywhere where this bottom is not 0. Okay, so you just got to watch out for, you always got to watch out for things that have quotients in them. The following functions are continuous everywhere at every point in their domains. So polynomials are always continuous. Polynomials real easy to deal with. Rationals are always continuous whenever the quotient's not equal to 0. Radicals are continuous. Okay, a square root function. You know, if you look at a square root function, it's going to look something like this. It's definitely always continuous here, and it has a limit right here when it's coming from the positive side, and so that thing is continuous. And trig functions are continuous, except where like tangent would not be continuous at pi over 2 because it has an asymptote there. These four functions, tangent, cotangent, secant, and cosecant, they're continuous everywhere except where they are undefined. Sine and cosine are always continuous. If f is continuous at c and f is continuous at g of c, then the composite function f of g of x is continuous at c. So that's pretty simple. Okay, so let's look at some of these. Describe the intervals upon which each of these functions is continuous. So f of x equals tangent x. Where would that be continuous? Well, tangent is discontinuous because it has an asymptote at pi over 2. So, and also at negative pi over 2. So we would say that this is continuous on the interval negative pi over 2 and pi over 2. And then every, I'm sorry, that should be open because it's unbounded on either side. And then I can add pi to each one of those intervals each time. So it's also going to be at, it's going to be open, or it's going to be continuous from pi over 2 to 3 pi over 2, and so on and so forth forever. Okay, let's look at g of x equals the sine of 1 over x when x is not equal to 0, and 0 when x is equal to 0. Now, one thing that you could do, because this is a little bit complicated thing to, most people don't know what that looks like, is I would go ahead and graph that and take a look at it. So you want to make sure you're in radians in your calculator. So make sure it's not in degrees. And then I would go ahead and type in sine of 1 divided by x and close the parentheses. Make sure you got no other functions in your calculator as well. Okay, and then I would go ahead and graph that. Okay, so this graph looks like this. Kind of goes like this. Oops, kind of goes up like this, and then down, down. It looks like that. And obviously it's got a hole right there at 0 because you can't plug 0 in there. But this tells you, hey, when it's 0, go ahead and plug that hole. Okay, so that would be a continuous function. I can draw that entire thing without picking up my pencil. Let's look at this next one here. H of x. Again, this is one I would probably graph. So x times the sine of 1 divided by x. And I'd probably zoom in a little bit on the center of that thing. And this graph appears to look like this. It's got a hole right here. And again, they're plugging that hole with a 0, so that would be continuous. Okay. So, as you can see, you must be able to apply the next theorem on both the multiple choice and free response sections of the AP exam. And since that's a bit distracting, we're going to go ahead and freeze that. The intermediate value theorem. If f is continuous on the closed interval AB, and f of A is not equal to f of B, and k is any number between f of A and f of B, then there is at least one number c on the interval from A to B such that f of c equals k. All right, what does that mean? This is one of those things that when you read a textbook, you need to probably go back and draw a picture of this to figure out exactly what it means. So here's what this means. I have a point A somewhere on this graph on the x-axis. So we'll call this A right here. I've got another point B, we'll say right there, okay? And then it tells me that f of A is not equal to f of B. So this function could be anything, but we'll say that it does something like this. Okay, so here's f of A. It is not equal to f of B. Now k, okay, so here's f of B right here on the axis, and here's f of A. Okay, now k is some point between f of A and f of B. So k is some number between here and here. It doesn't matter what it is. So we'll just put it right there. There's k. So what this means is there is at least one number c on the interval from A to B. So there's some number c along here where f of c equals k. And that would be right there. There's c. Okay. So you should be able to apply the intermediate value theorem on the AP exam whether the function is presented as an equation or as a table. All right, so one kind of easy example of this is something like this. Use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 on the interval between 0 and 1. Okay, so you're going to use this theorem to show that this function has to cross the x-axis between 0 and 1. All right, so how do you do that? Well, we're just going to go ahead and we're going to find f of 0. F of 0 would be 0 cubed plus 2 times 0 minus 1, which is negative 1. And then we're going to find f of 1. That would be 1 cubed plus 2 times 1 minus 1. That's 1 plus 2 is 3 minus 1, that's 2. Okay, now I know for a fact there has to be a 0 in there. How do I know that? Well, this is a continuous function. It is a polynomial, and they are all continuous. Okay, it's an x cubed. It's going to look something like this. Okay, and I can draw that thing entirely without picking up my pencil. So I know it's continuous. I know that it's negative at the point 0. And I know that it's positive at the point 1. So it has to take on every value between negative 1 and 2 between the points 0 and 1. So essentially, if I sketched a rough picture of this thing, okay, f of 0 is going to be at negative 1. And f of 1 is going to be at 2. Okay, I don't know what this thing does in between there. I don't care. All I know is that this thing goes from here to here on that interval, and so it has to cross 0 at some point in between there by the intermediate value theorem. Okay? And it could cross more than once, possibly. I mean, this could easily do something like, that, where it crossed 3 times. But I know that it does at least once. Okay. So that's it for today. Pretty short lesson. Here's some suggested problems for you to do. Remember to make sure to do some problems out of each section. I know this is kind of a long assignment, but get as much of it done as you possibly can, and I will see you at a later time.